Hello everyone, welcome to my youth programming club. Today we will be solving another daily LeetCode problem, and the problem's name is delete nodes and return forest. Okay, so you will be given a binary tree, and each node in this tree has a distinct value. Okay, and after deleting some nodes which we will be given by an array to delete, we will be left with a forest. Okay, and for those of you who do not know what a forest is a disjoint union of trees. Okay, and so after deletion of some nodes, you will be left with a forest from the given binary tree. So you have to return the roots of the trees in the remaining forest. Okay, and you may return the result in any order. And let's try to understand what the problem statement mean by this whole thing. So let's take this image or this example to the board and try to understand. So here the deletions that were required to make were nodes 3 and 5. Okay, so we were required to delete nodes 3 and 5. Okay, these were given by to delete function to delete array. Okay, so we deleted 3 and 5, but as you can see, when we deleted 3, this link is no longer active. This particular link is gone, and this link is also gone. So in a way you will be getting a new tree, basically three new trees. One will be this tree, one, then two, then four. Okay, and this will be one tree, and another trees will be six and seven. Okay, so these three trees you will be getting. So you have to return the roots. So root of these trees are nothing but 1, 6, and this 7. Okay, because this link also no longer active, these two links, because of deletion of. Okay, so you can see that the root was 1, then 6 and 7. So you have to return these. Now let's have a quick look at the constraints also before thinking of an approach. So according to the constraints, the number of nodes in the tree is at most 1000, and each node will be having a distinct value between 1 to 1000. Okay, both inclusive, and the number of nodes that are required to be deleted will be of order 1000. And it is mentioned that the nodes that will be required to be deleted will be having distinct values between 1 and 1000. Okay, so let's try to solve this particular problem. So what we can do here is, first of all, we can, you know first of all we need to know, while traversing this whole tree, let's say we are traversing this tree. Okay, so you can traverse in either DFS or BFS. DFS is depth first search and BFS is breadth first search. Okay, those of you who are hearing these terms for the very first time, I will provide links to explaining these techniques, articles explaining these techniques and their common use cases. Okay, in the description of the video, so you can definitely check them out. Here we will be using DFS. Okay, I just picked it for solving the problem. So what we can do here is, while we are traversing the tree with the help of DFS, we will check whether the node that we are currently visiting is required to be deleted or not. For that, we need to have lookups in the to delete array, and it will be wise to use a set instead of array, because it will reduce the lookup to order of 1 for constant time. Okay, that's why first of all the very first step will be to convert the delete array into a set for fast lookup. Okay, into a set for fast lookups. Okay, now once you are at a node and you know that it is to be deleted, then what you will do? If let's say you are at this node and you know that this is scheduled for deletion, then the very first thing that you will be doing is you will be breaking the link. This you will try to break these links. Okay, basically these three links you will try to break, and on top of that, all the subtrees of this tree will be informed that okay, now you are independent trees, and the root that you are having will be the a new root of your subtree. Okay, so tree should inform its parent children that they are now independent. Okay, so the second step will be inform children that they are independent. Okay, so this is the second step. And just before this step, what you need to do is, while you are visiting this one, you need to check whether any of the children of this current node 1 are scheduled for deletion. So if it is the case, then you would definitely like to break this link off, okay, prior to visiting those children that are scheduled for deletion. Okay, so in a way we can say that it will be 1.5. Okay, the step that I missed, or you can change the numbering. So it will be the third step. So the second step will be, if the children of if the child of, you can say, current node is scheduled for deletion, then you have to break the link between the current node and its child. Okay, then break the link. Okay, so this was the, let's say, current node, and 3 was its left child. Okay, and you can see that while we were at the current node, we came to know that okay, one of our left, it was the right child basically. Sorry, oh, right child. So we came to know that our right child is scheduled for deletion, so we will break the link off before visiting that child. Okay, and once we do that, then this child will become the current node, and it will inform its uh, children that okay, now you will be the independent ones, and it will also break the links from itself to its children's. Okay, so these three links will be broken. So this is what you will be doing recursively with the help of a DFS call. And once you, I again, would request you that you should be having prior knowledge of DFS. If you are not having knowledge of DFS, then I will urge you to go to the description box and find the article on the DFS there, and then come to the solution. Now, uh, proceeding further, now we will be doing all these things recursively. First of all, the very first thing we need not to do recursively, it is a one time thing, converting the to delete array into a set, and then we will inform the children. Then we will, for the current node that we are visiting in the DFS, we will check if any of its children is scheduled for deletion. If they are scheduled for deletion, then you will break the link between the current node and its children. Okay, and once you visit those nodes which were scheduled for deletion, you will inform their children also. Those nodes will inform their children that okay, now you are independent and you will be the new roots. Okay, so this thing will continue, and let's try to see how this thing can be achieved programmatically. So let's try to see the code and understand it. So let's take a fresh slide. So this is the code for this particular program statement, and yeah, let's try to understand what's happening here. So first of all, as I mentioned that we will be required to have a set for representing the nodes that are required to be deleted. So for that, I have declared a set for fast lookups, obviously, uh, and it will be initialized with the values of the to delete array. Okay, so once we are done with this step, then we will be starting to make our DFS call. So this method is using DFS technique. Okay, depth first search, and then there will be a current node that you will be visiting currently in the DFS. Okay, for that node, if this node is not scheduled for deletion and it is independent, then it means that it will be one of the roots, okay, of the in the forest. So you will add to the root nodes. So you will be basically having a list structure which will be storing the roots of the new forest trees. Okay, and you will be returning this root nodes post you completion of this make deletions method. Basically this make deletions method, what it does is it makes deletion, along with that it stores the new roots of the forest. Okay, uh, of the trees in the forest that will be resulting because of those deletions that we will be making. Okay, so then if this is the case that the current root is independent, the current node is independent basically, and it is not scheduled for deletion, then you can say that okay, it will be root of one of the trees in the forest, and you will add it to the root nodes list. Okay, now proceeding further, uh, you will declare a boolean variable to make to store whether you have to make its the children of the current node independent or not, depending upon whether the current node is scheduled for deletion or not. Okay, and also on top of that, as I mentioned, that there might be some situations when let's say you are at this node and one of its children or both of its children are scheduled for deletion. In that case, you would like to break this link of this link I am talking about. So in order to still have the values of its children, we are storing them in some variables. So the left child and the right child will store the uh, addresses or the references to the left and right child of the current node. So once we are done with all this, then we will see whether the current node is scheduled for deletion or not. If it is scheduled for deletion, then you will say okay, we need to inform its children that they are now independent, and we need to pass it down. So we will change the value of make child independent to true. Then we will check for the condition that if let's say the children of the current node, irrespective of the fact whether current node is scheduled for deletion or not, are also scheduled for deletion or not. If any of the child of the current node is scheduled for deletion, then we have to do this step of breaking the links with the children's. So we are doing it here. If first of all the current node should be having either a right child or a left child in order to break the link between from the node and the child. Okay, so if left child is there and it is scheduled for deletion, then you will break the link between the left child of the current node and the current node. Okay, and similar thing you will be doing for the right child. So once you are done all this, then you will recurse for the left and right subtrees, and also pass this make children independent variable. Depending upon whether you have changed its value or not, it will be passed, and this thing will keep repeating. And once you have done traversing all of the nodes in the current tree, then you will be having the roots of the trees in the forest that will be resulting as a deletion of nodes in the given binary tree. So you will simply return your root node. So this is all in this implementation. And if we talk about the complexities, time complexity wise, it's order of n. Okay, where n is the number of nodes. Okay, because in this particular DFS call, we are visiting each node a constant number of times, so it is order of n. And for the space complexity part, uh, it will also be order of n because of use of the recursion stack. Okay, and yeah, and this root nodes also, in a way we can say that it will be summing up to overall order of n. Okay, so these will be the complexities, and this is the whole approach and the implementation. If you are still having any kind of doubts or any queries in general, then you may ask them in the comment section. And I really hope this solution walkthrough added some value to your journey of honing your DSS skills. I will see you in the next video. Till then, keep practicing more and more problems. Thank you for watching.